You clicked because you have seen too many robots fail after months of training. The real problem is not that our AI is too weak, but that we are using it where it does not belong. Most automation projects collapse because engineers try to solve simple mechanical problems with complex neural networks. By the end of this explanation, you will understand why adding physical constraints often saves more money than adding more data. Consider the current state of industrial robotics. We are witnessing a massive wave of over-engineering where every task is handed off to a deep learning model. The industry assumes that if a robot can learn, it must be better, but the data tells a different story. Research from the AI study reveals a significant gap between what we hope AI can do and what it actually delivers in a factory. The findings show that 80% of deployment failures stem from attempting to learn tasks that are mechanically solvable but computationally expensive. When we rely on black box models for routine operations, we invite a specific type of failure that deterministic logic simply cannot produce. The core issue lies in the nature of neural networks. They are probabilistic systems designed to find patterns in noise. They do not understand physics, cause and effect, or safety boundaries in the way a human engineer does. They hallucinate. In a controlled simulation, a neural net might learn to pick up a part perfectly. But in the real world, a slight change in lighting, a speck of dust, or a minor variation in friction can throw the entire model off. Because the network has not seen that specific variation during training, it does not know how to react. It might apply too much force and crush the part, or it might drop it entirely. This is the hallucination space where neural nets fail, a zone that exists whenever the environment deviates from the training data. Now consider the alternative approach that is often ignored. This is the use of hard-coded mechanical constraints. Imagine a robot arm with physical stops, limit switches, and rigid guides built into its end effector. These are dumb solutions. They do not learn, they do not adapt, but they are absolutely deterministic. If a part is out of position, the mechanical stop prevents the arm from crushing it. If the force exceeds a threshold, the limit switch cuts power instantly. This is not about being clever, it is about being safe. By replacing 80% of the learned policy with these physical constraints, we eliminate the possibility of catastrophic failure. The robot is no longer guessing. It is following the laws of physics and the design of its own hardware. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This brings us to a critical insight that many engineers miss. The simulation to reality gap is not just a software problem, it is a fundamental mismatch between subsymbolic learning and industrial requirements. In the real world, safety and reliability are not optional features. They are the baseline for any project that needs to return an investment. When you deploy a pure end-to-end learning system, you are asking the robot to infer the correct behavior for every single millisecond of operation. You are asking it to handle edge cases that were never seen in training. The result is a system that works 99% of the time but fails catastrophically the other 1%. In an industrial setting, that 1% is enough to shut down a production line and cost thousands of dollars. So why do we keep doing this? The answer lies in the allure of generative AI. The narrative suggests that we can just throw more data at the problem and the robot will figure it out. This ignores the reality that data is expensive and that real-world environments are infinitely variable. A neural net requires massive datasets to cover all possible variations. A mechanical constraint requires a single physical design decision. The trade-off is often ignored in favor of pure learning because it sounds more impressive. But when the lights go out and the line stops, the impressive model does not fix the problem. The simple constraint does. There is a middle ground that is gaining traction among the most successful teams. This is the neurosymbolic architecture. In this hybrid approach, AI handles only the high-variance perception tasks, such as identifying where a part is or recognizing its orientation. Once the robot knows where the object is, the execution is handed over to traditional control theory and mechanical constraints. The AI says where, but the physics says how. This separation of concerns allows the system to be flexible where it needs to be, but rigid where it must be safe. It is the convergence of the best of both worlds, acknowledging that while AI is powerful for perception, it is brittle for execution in unstructured environments. The evidence from scientific discovery adds nuance to this argument. In high-complexity tasks, such as those managed by the Genesis robot for autonomous scientific inquiry, the sheer number of variables can exceed the capacity of simpler mechanical solutions. Here, AI is essential because the task space is too large for any human to program explicitly. However, this is the exception, not the rule. For standard industrial manipulation, the frontier of autonomy does not require us to abandon mechanical constraints. It requires us to be honest about where AI adds value and where it adds risk. This shift in perspective changes the career landscape for robotics engineers. Those who focus solely on deep learning often find themselves overfitting their models to simulations that do not exist in the real world. Engineers who master traditional control theory and mechanical constraint design are increasingly valued. They understand that the most robust system is often the one that relies least on the machine's ability to learn. They know that a well-designed physical guide is a better safety net than any algorithm. This is the intellectual honesty that separates hype from reality. We must stop trying to make machines think like humans and start making them act like machines. The path forward is not to abandon AI, but to use it with surgical precision. We must stop trying to learn everything. We must stop assuming that a neural net is the only solution to a complex problem. The most reliable automation systems of the future will be hybrids, where the certainty of mechanics meets the flexibility of perception. This is the only way to bridge the adoption gap and move from failed pilots to deployed reality. The future of robotics is not in the black box. It is in the intersection of the physical and the digital, where every constraint is respected and every failure mode is designed out before the code is ever written. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.